So my name is Connor Bybee. I'm a graduate student at the Redwood Center for Theoretical Neuroscience at UC Berkeley. I'm advised by Fritz Sommer, and this work was supported by the Neuromorphic Computing Lab at Intel Labs. The title of this talk is Optimal Oscillator Memory Networks, or Optimal Oscillator Associative Memories. I'm not sure which one is best. I've been going back and forth. This work I will present is useful because it connects algorithms and hardware. Specifically, it examines the computational properties of attractor networks and their implementation in a physical system. Attractor models are important in neuroscience and are becoming increasingly important in machine learning. In neuroscience, these models serve to describe observations from the hippocampus and other brain areas. Associative memories are also useful for error correction and vector symbolic architectures, which were presented earlier by Chris Kim and Dennis Clayco. Other associative memories include modern hot field networks and the transformer networks. This talk will focus on autoassociative or recurrent networks corresponding to a system with feedback and their implementation in oscillator networks. Many traditional attractor models are inefficient. That is, their capacity with respect to some metric is low, and there may not be a practical hardware implementation. This raises some important questions. How to design efficient associative memories for neuromorphic hardware, such as networks of coupled oscillators. In addition, we want to consider the compatibility or flexibility with which an algorithm can be mapped to hardware. This is important given the diversity of the neuromorphic platforms and the underlying neuron models, such as leaky integrating fire, resonating fire, or the Hodgkin-Huxley type model. Attractor dynamics have been shown to implement content-addressable associative memories, where memories are stored as basins of attraction in some energy landscape. Remembering or recall is performed by allowing the network to converge to a stored attractor. Attractors can take several forms and may be dynamically stable. That is, a dynamic state which corresponds to some fixed point in another space. I'll explain this in detail later. To understand associative memories, I'll first describe the binary Hopfield associative memory, or the classical Hopfield associative memory. The associative memory consists of a network of units, or neurons, and each unit is allowed to take one of two possible states. Here, -1 or 1. A memory or pattern is a high-dimensional vector. Like the state variables, each element in the pattern vector can take one of two possible values. Hebbian learning is used to store a set of patterns distributed through the network in the synaptic weight matrix. The outer product is commonly used and is a sum of outer products of the individual patterns. The system is described by an energy function. Stored patterns will have low energy, and states which don't correspond to stored patterns will have a relatively higher energy. The energy governs the system dynamics. The change in the neuron state turns out to be a function of the negative gradient of the energy with respect to the neuron state variables. The activation function usually quantizes the neural state, and here the activation function just returns the sign of the presynaptic input. This figure demonstrates how an associative memory can perform error correction. So starting with a corrupt pattern, the dynamics will move towards the closest critical point. In this particular figure, there are two types of critical points, those corresponding to stored patterns and those corresponding to spurious states. Successful decoding happens when the network converges to a stored pattern, and an error occurs when the network converges to a spurious state. So then you see that error correction has two components, one of collective state computation through the synaptic weight matrix, where information is passed around through the network to perform cleanup, and then locally in the form of the nonlinear activation function here in the state quantization. The associative memory we'll discuss can be described by relatively few number of parameters. The number of stored patterns, M, the number of neurons or units in the network, N, the number of synaptic connections or network parameters, S, and the information per pattern here, I sub p, defined in the bits per pattern. These parameters determine the resource requirements and capabilities of associative memories. For example, the number of neurons determines the size of the network. The number of synapses and connectivity determines the memory requirements, as well as the connectivity and communication. And the information per pattern and the number of patterns directly affects the functional capabilities of an associative memory. So here we'll define some key metrics to be efficient, such as the pattern capacity and the information capacity. The pattern capacity will be defined as the number of patterns stored in the network divided by the number of units or neurons. The information capacity will be defined by the information per pattern times the number of patterns divided by the total number of synapses in the network. Associative memories have been around for a while and extensively studied in the literature. There's a diverse set of models, each with varying properties. The state variables in associative memories can be complex or real value, discrete or continuous, and the pattern activity can be sparse or dense. It's important to consider that even if the stored patterns are discrete, the state variables themselves can be continuous. For example, in the binary Hopfield case, these patterns take the values of typically -1 or 1, but depending on the algorithm implementation, the state variables may continuously vary from -1 to 1. The dense Hopfield network has a relatively high pattern capacity or entropy information per pattern, but it has a relatively low pattern capacity and information capacity. That is, the number of patterns that can be stored in the network is relatively low, and therefore the total information per synapse is relatively low. Sparse patterns, on the other hand, have a relatively low pattern capacity, being sparse, but the network allows for a large number of these patterns and a high information capacity. Now, maybe not known to everyone is that there's also complex, dense, and continuous networks. And then these networks have a relatively high information capacity, taking continuous values in the complex space. But it turns out that such networks actually have a low pattern capacity or information capacity. So, open question is there a way to outperform the traditional binary Hopfield network, achieving both a high pattern capacity and information capacity and a high pattern information or entropy per pattern? And so, in this work, we will discuss complex, dense, and discrete associative memories, which do obtain a high pattern capacity. So first, I'll introduce complex valued phasor associative memories. Phasor associative memories were first presented by Nost in '88. Compared to the Hopfield network, phasor and associative memories store complex valued patterns, continuous patterns in the complex space. The learning is similar to the Hopfield network, except now the conjugate transposed is used in the outer product learning rule. The energy, again, is very similar, except the conjugate transposed is used. The dynamics are similar, again, but the activation function now projects the complex values onto the unit circle, preserving phase information. The two figures here on the right show this and how that Zi can be represented as a complex exponential with unit magnitude and a phase variable phi psi. The figure in the bottom right compares the pattern capacity of continuous phasor associative memories to Hopfield networks. We see for Hopfield networks, we can recover a well-known capacity close to 0.14 or 0.139 patterns per neuron, but the continuous valued phasor network does not achieve nearly such a capacity. So it goes to show that maybe there's a way to modify these complex representations to achieve a higher pattern capacity. So we'll consider phasor associated memories with a discrete number of states on the unit circle. Complex state space allows for an arbitrary number of these discrete states represented as phases of complex valued phasors. This is the same as phase shift keying in the communications literature. Here I've shown QPSK, or 4, Q equal to 4, in these Q state phasor associative memories. Learning is still the same as the complex outer product, but the activation function now is different. The activation function quantizes the phase of the presynaptic input to the closest phase angle on the unit circle. Now, this representation trades off pattern complexity for error correction. You can see that for QPSK compared to 8PSK, the amount of noise required in the presynaptic input must be larger before an error. For APSK, we see that we can obtain a higher entropy or bits per neuron, but that the relative amount of noise needed to cause an error is less. So, what is the optimal choice? 3. Our main contribution is reproducing results which seem somewhat forgotten from the literature. Cook in the 89 uses mean field theory to compute the pattern capacity and information capacity, which accurately predicts the results shown here. Here, we must distinguish between the pattern capacity and information capacity. Q equals 3 achieves optimal performance in both metrics, both the pattern capacity in the terms of the patterns per neuron and the information capacity in the bits per synapse. For Q equals 2 and 3, we can see that both obtain the same pattern capacity. They can store the same number of patterns, but Q equals to 4 has a greater number of bits, being 2 bits per neuron, and therefore obtains a higher information capacity. We see that for many values of Q, we can obtain a higher value or higher information capacity than the traditional Hopfield network. So we may want to map these Q-state phaser associative memories to a neuromorphic hardware. So we'll examine oscillator networks. It's not exactly clear how to map these Q-state phasers when the number of Q is greater than 2. So it's possible to map discrete time, iterative update, associative memory algorithms to continuous time dynamical systems. And oscillator networks are a natural choice. Many oscillator networks can be reduced to the Kuramoto model. This system is described by an oscillator with a fixed magnitude in a dynamic phase. Shown here is a network of coupled oscillators with identical coupling. Starting with random phase in the initial condition, we quickly see that the dynamics synchronize the network to one of the stored patterns. In this case, just there's one pattern, it's all one. In general, the synaptic weights in the Q-state phaser are complex valued. So it was not previously shown how to map these matters to the Kuramoto model. A simple Kuramoto model consists of real value coupling, but we can take the magnitude of the synaptic weights and map those to the coupling strength, and also the phase of the synaptic weights and map those to a fixed phase shift within the Kuramoto model here. When the number of patterns in the network is non-trivial, so for m greater than 2, it turns out that the fixed points of this dynamical system are not the stored patterns. So even when starting with the stored pattern here for Q equals to 3, the network quickly diverges to a fixed point, which turns out not to be a stored pattern, as seen here over time as the similarity just gradually decreases. And this reproduces similar results from the NOST 88 paper. So then the question comes to, how can we perform phase quantization in this dynamical system? And it turns out to be a non-trivial problem, because if we examine the phase quantization activation function, it requires computing the distance to all possible discrete phases in a search to find the minimum phase, and then project and then take that phase. But it turns out that we can use some ideas of nonlinear oscillators and the idea of harmonic injection locking to perform this phase quantization, where we use a network of oscillators and a nonlinear ratio between those here, Q, equal to the frequency of the harmonic injection over the fundamental frequency, or the frequency of the memory network. And the graphic on the top right demonstrates how such a network performs this phase quantization. So given a memory network oscillating at some frequency omega, we can inject a signal at some harmonic frequency here, 3 omega. And we see that of the 3 possible allowed states, this corresponds to a phase aligning of the modes of the fundamental with the harmonic. And the figure on the bottom demonstrates this network for our Q-state phasor associative memory. As we gradually, starting with initial conditions and no harmonic injection, the network will begin to diverge from a stored pattern. And in this case, the stored pattern actually had corrupted noise. As we increase the amount of coupling for the harmonic injection, we see that the network quickly converges to one of the 3 possible phase states. So back to our main result, we have Q-state oscillator networks, and the complete dynamics can be described by this phase equation corresponding of a Kuramoto type phase coupling and a harmonic injection type phase coupling. And so for Q equals to 3, again, we can see that started with a corrupted pattern. This network will quickly converge to one of 3, all the neurons in this network will quickly converge to one of the 3 possible phase states, and the similarity will move back up to the stored pattern, indicating that the fixed points of this dynamical system are the stored patterns. One thing yet to examine is the capacity of these Q-state oscillator models. One thing we can examine is potentially the dynamics also of this coupling function H. So here I've stored a number of patterns up to capacity for this network. And indeed, we show that depending on the initial conditions, we can indeed still perform error correction and move the fixed points of the dynamical system to the stored pattern. And future work will examine general phase coupling functions, which will allow these networks to be modeled on other types of oscillators, again, such as leaky integrate and fire oscillators, resonate and fire oscillators, and Hodgkin and Huxley type models. Here I've shown a phase diagram, phase response curve for a Hodgkin and Huxley type model, where depending on this phase difference phi j minus phi I, the amount of phase shift coming through this coupling function changes, which is different than the original Kuramoto model. And so completing why Q equal to 3, and does this result hold for other systems? So for fun, I simulated a common channel coding experiment using MRA PSK. The goal of this experiment is to test for different signal-to-noise ratios the bit error rate for given energy per bit over the noise of the signal. And again, I find that Q equals 3 is optimal. And this result not only is grounded in mean field theory, but now is in communication theory. So it goes to show that potentially there is a way to design efficient, optimal associative memories for neuromorphic hardware. And this will have maybe practical applications also in communication. In summary, dense hot field associative memories in the literature have low capacity. Here we've shown that Q-state phasor associative memories achieve a higher capacity, and that their implementation of these Q-state associative memories can be implemented in coupled oscillators with harmonic injection. And again, Q equals 3 is best. And with that, thank you for listening to my talk. I would like to thank those that helped me with this work, my advisor Fritz, Alex Belston, who helped with a lot of the figures, and many conversations with Dennis, Paxton, and Bruno, as well as Dmitry Nikonov at Intel Labs with helping with these oscillator simulations, and the funding from the NSF and the Intel Labs Neuromorphic Computing Lab. Thank you.